Well, Riyadh, my philosophy towards LaTeX is once you get good at it, it gets a lot easier. There is definitely a learning curve for LaTeX. But once you get used to it, you basically set up like an align environment, and then you just start copying, pasting equations, making a small edit to show your work every line. And then like, oh my gosh, it's very easy to spot mistakes later on. You can use Vim with LaTeX and snippets if you want. I don't know. I might be willing to provide the circuits in LaTeX. It just requires more work on my part, which I'm not really in a capacity to promise. All right. We have meet my threshold voltage of 30 student volts. So let's give just a few more seconds on this poll. I am very curious because I've thumbed through the documents. I did not get really anywhere with grading yesterday for the first homework assignment, but it's marking them up for grading is going to be a big pain. All right. Is every question graded for accuracy? I mean, yes. I mean, like, right answers do matter. And Aubrey has a poll for the class. What is everyone's favorite editing tool for using a USB pen pad? So, all right, ending poll. Sharing poll. So it's pretty neck and neck, we have 90% of the class basically split evenly between scanning handwritten documents and using something like Microsoft OneNote, where note-taking, freeform, PDF editing, notebook editing, what have you. 2 people are using Microsoft Word. I'll let you know. I don't want to throw them under the bus, but my TA decided to start the solution manual in Microsoft Word, and I'm gagging a little bit because it's just so awful to use the equation editor and everything. So I'm going to try to dissuade them from more Microsoft Word in the future. Personally, I use LaTeX for everything. Like literally everything. You see it in my slides, my syllabus. You'll see it on the exam too. I think it's really clean, especially when you use circuit ticks for circuits. One person's using Markdown. Good for you. I think Markdown is a fairly capable tool. Add LaTeX into Google Docs. Yeah, I might ask you more about how you do that, Aiden, because that would be great. We're using OneDrive for everything right now, and like it's a little icky. And okay. And then one person's doing other. So the person who said other, do you want to explain what you're using for homework workflow? If not, that's okay too. But okay, that's kind of what your peers are doing. Okay. Let's go ahead and I should have chosen OneNote. That was a mistake. Okay. All right, let's go ahead and start presenting. Adrian, you're really trying to throw me off with your name today, and it's like, what's going on? Oh, it's okay. So last time we covered, an introduction to solving differential equations, specifically ordinary differential equations by, classical techniques. And then today we're going to start applying it to circuits. So we talked about our structure of the ordinary differential equation, constant coefficients, linear combinations of time derivatives, and an order of the function and the forcing function. And we're using exponentials because we know it'll be a nice and easy way to get answers. And then we broke it into the homogeneous or natural solution and the particular or forced solution. So again, the natural solution is a family of functions where the result of adding, multiple, the family of functions to, our solution x of t doesn't really change anything because it's adds zero contribution to building up the function on the left-hand side. And what's going on here? Okay, these arrow keys. We talked about the characteristic equation, where as a shortcut, you just replace every time derivative. The order of the time derivative becomes the power of lambda in the ODE, and you set it equal to 0 to find the roots, which gives you the form of the homogeneous solution, sum of a to sub k e to the lambda sub kt from 1 to n. We worked through examples. And then we talked about you can use an initial value problem. However, you shouldn't use the initial value problem, initial conditions, to find the homogeneous form coefficients until you deal with the forced solution. So for the particular solution, we said that we have to guess the functional form that the particular solution will take. We need one for every term in our forcing function. And we talked about how you match basically step functions with step functions, exponentials with exponentials, same base. If you have a mix of both, you can do mix of the different exponential bases, or you can use, in this case, where they're equal and opposite hyperbolic functions. And then if you have, cosines and stuff like that, or sines, you have to use both cosine and sine terms. Or you have just one cosine or sine term, but with a phase shift. Because in general, you will introduce a phase shift when you apply a sinus one. Then we worked through this particular solution example where we matched the functional form and plugged it back into the ODE. Then after you do derivatives and some algebra, you're able to get the coefficient in front of your particular solution. Then we talk about the complete solution where you put everything together. And then special cases, when we have a repeated root in the characteristic equation, we must include multipliers from the next power term in the power series of t. And similar deal a second pass, when we check for forcing function matching the homogeneous solution form. Then we went through the procedure where we find the characteristic equation, solve it to find the form of the homogeneous solution. Solve for the coefficients of the particular solution, and then use initial conditions to resolve ambiguity of coefficients in the complete solution. We worked through this nice example. Then we worked through an example where we had a matching form of our forcing function to the homogeneous solution. So we used a multiplier of t in our particular solution. And then, we worked through this much harder example where we, dealt with, a cubic equation where we used rational root theorem to help find the roots. Then we had to use a multiplier in our homogeneous solution and a higher multiplier in our particular solution. The derivatives became messy when we substituted our form of our particular solution into our ODE, but we were able to solve for coefficients, write the complete solution, use our initial conditions in our complete solution, and then solve a system of three linear equations to figure out the coefficients to our initial value problem. You won't see anything harder than this on homework because, yikes, this was already a mess and it took me a long time to figure out how to do this correctly. That brings us to today. Any questions? Hearing no questions, we'll go ahead and start with today's lecture content. So we're going to start with what's called first order circuits. So these are circuits where they have one reactive element in them. And, the two classes are basically RC circuits and RL circuits, where, R stands for resistor, C for capacitor, L for inductor. So we'll start with the RC circuit, and specifically with the series RC circuit. So it's as simple of an RC circuit as you can get. You have a voltage source providing this, step function V, where basically that just means, the input forcing function is a constant V for all of time past t greater than 0, as this little note says. And we have this resistor with current IC of t flowing through it, and then we have capacitor with voltage VC of t here. Note that there's no initial conditions given for the capacitor, nothing in our instructions, nothing was marked on the side of our circuit diagram. So we assume that the circuit is at rest at t equals 0 minus. Equivalently, there is no voltage across the circuit right before time t0, no voltage across the capacitor, I should say, and no charge stored on the capacitor plates at time equals 0 either. So either way of thinking of it works. So we're going to do some symbolic analysis because we're going to see the RC circuit again and again and again and again in this course. Same with all these first order circuits. So we're going to deal with things symbolically. It's kind of the Michael Hayashi way. And, we'll plug in some numbers later when we want to gain greater intuition. So of what, the responses actually look like. So basically, we need to figure out how to write a ordinary differential equation for this circuit. And there's, different voltages in the circuit, but there's one current shared by all the circuit elements. So that tells us that, we should, write a KVL equation. And to do that, we need to know how we get the voltages across each of our circuit components. So Ohm's law says that the voltage across the capacitor as a waveform is equal to the resistance times the current through the resistor as a function of time. And notice the capacitor current is the same as the resistor current. So we've already made that substitution here. Hopefully that doesn't throw anyone off. And then we need, the defining equation for the capacitor. It's the constitutive equation. It's the thing that relates our circuit variables to each other, current and voltage, the IV relationship. And that is the current through a capacitor as a function of time is equal to the capacitance times the derivative of the voltage with respect to time. So by KVL, we get Vn of t equals, that voltage rise is equal to voltage drops. VR of t plus Vc of t. We can plug things in and we get the equation at the top of page, which is our ordinary differential equation. We're going to see this again and again, so it's definitely worth, tucking away in your brain. So Vn of t equals Vc of t as the last term. In the first term, we said that it's going to be VR, which is R times IC of t, but we can substitute IC of t with C times dVc dt. So notice everything here relates capacitor voltage to a forcing function. So the next thing we need to do is neglect the forcing function. To find the homogeneous solution, 0 is equal to RC times dVc of t dt plus Vc of t. So this characteristic equation, we get 0 is equal to RC times lambda plus 1. Because the coefficient in front of Vc of t is 1. Solve for lambda. Lambda is equal to -1 over RC. This lambda is going to show up again and again and again. So definitely worth being able to, solve it, in your head without having to write it down. So we'll write the homogeneous solution as V sub C H of t is equal to A e to the -t over RC, where A is an undetermined coefficient. We don't know what it is yet. We would need the initial values to figure out what it should be after we find the particular solution. So the particular solution, V sub C P of t, is equal to some constant D times U of t, where we got to figure out what this constant D is. And it's just, a constant after time t equals 0 plus. So we'll substitute into the ODE, take the derivative and solve for D. We did this a lot yesterday, so I'm combining steps. So we'll get, forcing function V times U of t plus RC times 0 plus D U of t Well, this is just 0 because we're taking the derivative of a constant function. So we're left with d is equal to v. So our complete solution, v sub c of t, sum of the homogeneous particular parts, is a e to the negative t over rc plus v times u of t. We can solve for a, knowing the circuit is at rest at time t equals 0 minus, and capacitor voltage cannot instantaneously change. So VC at time equals 0 is just 0. We get this from the constitutive equation that capacitor voltage cannot change instantaneously. It's basically an integral of a current. And, even if the current jumps and spikes, the capacitor voltage between two time instances should be continuous. So 0 is equal to a e to the negative 0 over rc plus v. Remember, e to the 0 is 1. So we get that a is equal to negative v. So we'll rewrite our complete solution to capacitor voltage. We'll leave a u of t at the end and just say it's v times the quantity 1 minus e to the negative t over rc, an exponential approach. So at time t equals 0, if there's 0 volts, and then it's going to grow and exponentially approach the value of v. Now, hopefully you've seen this type of relationship before in ECE, 20,007 lab. But if it's new to you, like, you can just plot this out with these particular values, and you'll get, this sort of example here. So we'll use a step function of 5 volts, a 100 ohm resistor, and a 0.1 farad capacitor. These are unrealistic values. You can choose more realistic values in your parts kit if you want to just build it with your breadboarding kit. So you'll get, lambda is equal to negative 1 over RC, or negative 0.1 units of resistance times capacitance, which is just seconds in the denominator. And then V sub CH of t is this, where, I've rewritten the times, negative 0.1 t with 10 seconds in the denominator. D is 5 volts, A is negative 5 volts. So the complete solution to the capacitor voltage as a function of time is 5 volts times the quantity 1 minus e to the negative t over 10 seconds times u of t. And there's your answer. What questions do we have about this series RC circuit? RC stands for really cool, RL for really lame. Yeah, exponential decay is always really cool, and we'll see in the RL circuit that we'll still have it. So if we take t is equal to 0 minus, then isn't u of t 0? Yes. You are correct. However, I'm trying to think why. I guess what's the conceptual hang up? At t equals 0 plus, Vn becomes V, and this circuit, also still stays at a value of 0 at time equals t equals 0 plus. You'll notice that, yeah, it's 1 minus 1 at time equals 0 plus, so it's still a 0 value. How is V u of t equal V when t equals 0 minus? It is not. It is a value of 0. We looked at time equals 0 plus. We looked at, circuit is at rest, and the capacitor voltage is at 0 at t equals 0 plus and t equals 0 minus. So that voltage literally does not turn on. The forcing function does not turn on until time equals 0 plus. Does that answer your question, So-Won? Everything you stated was correct except for that last question you had. or, got it. Good job. Any other questions about the series RC circuit? Hearing none. The dual of a series circuit is a parallel circuit. So here is the parallel RC circuit. And now we're going to use a current source and have the R in parallel with C. They'll have different currents through them. And, we'll use a step function here, find VC of T. You notice this is just a source transformation of the series RC circuit. Whereas here, basically we had, a Thevenin representation, voltage source with a series resistance. Here we have a Norton representation after source transformation, where we have a current source with a parallel resistance. Or conductance, if you want to think about conductance. G is just 1 over R. So if you write a KCl equation, you'll get that the input current is equal to IR of T plus IC of T, which is 1 over R times VC of T plus C times dVC dt. And if you go through the same work, for the step function input, we get that VC of T is equal to R times I times the quantity 1 minus e to the negative T over RC times U of T. Notice we have the exact same lambda appear in our circuit. Our lambda of, negative 1 over RC still appears in the circuit, and it's still an exponential approach. So overall, we get very similar behavior as we would expect when we just take a Thevenin equivalent or a source transformation of the previous circuit. And V is just R times I, matches our source transformation expectations. Questions about this? Why is it 1 over R? Okay, so by Ohm's law, the current through this resistor, I sub R of T, is just V of this resistor, which is the same thing as VC of T, times 1 over R. No worries. It's still early. So now we'll talk about the RL circuit. So we're going to ask you to find the current in this inductor, IL of T. It's a shared current by all the circuit components. We'll have the input voltage be a step function V times U of T. We'll have VL of T, VR of T for values L and R. We don't give you any initial conditions of the inductor. We don't give you any initial inductor current or the initial, amount of magnetic flux linked by the inductor. So we can just say that the circuit is at rest at T equals 0 minus. It'll become active at T equals 0 plus because of the rapid change in our forcing function. And again, Vn of T is just V for time T equals or T greater than 0. Note, this is just the dual of the parallel RC circuit. So what do I mean by dual? The current source became a voltage source. The parallel resistance became a series resistance. Capacitance became an inductor. And notice that, it went from being in parallel to in series. Everything is the dual concept. Remember, you only need to know half as much as you need to know of ECE 20,001 to know the other half if you can understand the concept of duality. So in true Michael Hayashi fashion, we're going to look at the symbolic analysis of the series RL circuit. So again, we need Ohm's law, VR of T is equal to R times I sub L of T. And the constitutive equation for an inductor. This is the defining equation for an inductor. Something that we should all know and love is that V sub L of t is equal to L times dIL of t dt. So there's a voltage across the inductor proportional to the derivative of the current running through it, where the proportionality constant is just what we call inductance, L. By KVL, we get Vn of t is equal to VL of t plus VR of t, where VR of t is just R times IL of t. And, VL of t is, this equation, the constitutive equation, basically directly. So we'll neglect the forcing function, find the homogeneous solution. 0 is equal to this. And then by the characteristic equation, 0 is equal to L times lambda plus R, where you replace the time derivative with lambda, and then the function itself with just the number 1. And so we get lambda is equal to negative R over L. Again, this value is going to show up time and time and time again, so it's worth knowing how to get this ODE, in your head, and knowing that we're going to get a lambda value of this time and time again. So we'll get the homogeneous solution. I sub L h of t is a e to the negative R over LT. And then we'll assume the particular solution is just a constant times the step function, so just a constant after time t equals 0 plus. Substitute into the ODE, take the derivative, solve for d, and again, at time equals 0 plus, this is just going to give you a 0 here, because you're taking a derivative, and 0 plus, these just become 1. So you get d is equal to v over r. Write the complete solution as such. Solve for A, knowing the circuit is at rest, and similar to capacitor voltage, inductor current cannot instantaneously change. Remember, it's an integral of the voltage across it, and integrals will help produce nice continuous functions. So the inductor current at time equals 0 plus must also be 0. So A times e to the 0 is just A, and then plus a v over r. So we get A is equal to negative v over r. So our complete solution to the circuit current is the inductor current I sub L of t is v over r times the quantity 1 minus e to the negative r over LT times u of t. And again, if you've been diligent about keeping track of your units, which some of you would really benefit from being more diligent about keeping track of your units on homework, v over r is units of current. 1 is a constant, and here is a constant. So we get, units of current overall. R over L has units of 1 over time, or so 1 over seconds, and then t's in seconds. So that means the exponent should always be a unitless, number, just a number. So yeah, units work out. What questions do we have for the series RL circuit? Step 8 in more detail. Okay, Aubrey? So we have IL of P, or I sub LP of T is equal to just, our assumed form for a step function input, which is D times U of T. We plug this into the ODE itself. So we're going to get IL of T. So take the derivative of something that's just a constant after time equals 0 plus, and you get something that is 0. So that means, we'll get L times 0 on one side. And then we'll plug in our forcing function to the left side of the equation. So that's just V times U of T. And then we'll take R times IL of T, where IL of T is just D times U of T. So we'll get R times D times U of T. Again, we're solving for a time greater than equal to 0, or I guess strictly greater than 0 if we want to avoid any weirdness. So we'll just get V times 1 is equal to L times 0 plus R times D times 1. Or D is equal to V divided by R. We just solve for the unknown coefficient D. You're welcome, Aubrey. Any other questions? Oh, I guess I do have a numerical example I'll go through. So let's say, our input is 2 U of T volts. We have a 100 millihenry inductor, and we have a 0.1 ohm resistor. Find, lambda is equal to negative R over L, and you'll get negative 1.0 units of 1 over seconds. Rewriting it with, a pure denominator instead of, I guess numbers divided instead of numbers multiplied, we get the homogeneous solution is A times e to the negative t over 1.0 seconds. And we get that D is going to be equal to 20 amps, where that is just V divided by R. And then A is equal to negative V divided by R, or negative 20 amps. So the complete solution is IL of T is equal to 20 amps, a really big current, times quantity 1 minus e to the negative t over 1.0 seconds times U of T. And that kind of makes sense that we have such a large current because we have a very small resistor, very, very small resistor, and we have an inductor that is rather, rather large. Any more questions about the series RL circuit? Why is the current negative? The current is never negative at any point in time. If we plug in t equals 0, we will get that we have 1 minus e to the 0 is 1. So we get a value that is 0 overall. This is an exponential approach. So if we apply t equals 1 seconds, we'll get 1 minus e to the negative 1, 1 minus 1 over e, which is another, as a quantity, that's a positive number. So it's going to get you something overall that at that time less than 20 amps. And as t goes to infinity, e to the negative infinity, you can think about your exponential decay graph, or you can think about the far left-hand side of your exponential growth graph, and you get that, this entire power is equal to 0. So you'll just get 20 amps. So this current is never negative tangent. Does that make sense? Good. Everyone's kind of chugging along then. So next, we'll do something that's a little bit more exciting now. So we're going to do a parallel RL circuit. So again, I guess this would be the dual to the series RC circuit, where now we have a very exciting, I guess, relatively exciting In of t, our forcing function, is now an exponential. So In of t is now I1 e to the bt times U of t, where it is given that b is not equal to negative R over L. So note we're not given any initial conditions, so we're asked to find, this time instead of IL of t, VL of t. Okay, so here's how we do it. Ohm's law tells us that the resistor current is 1 over R times, the voltage across the resistor, which is VL of t. And then VL of t is equal to L times DIL dt. So by KCL, the current into this node must equal the current out. So In of t is equal to IR of t plus IL of t, where IL of t is, we're going to treat that as the quantity we're going to solve for initially. And then we're going to say, well, okay, we'll have 1 over r times L times dIL dt. So we get this term as L over r times dIL dt. So notice we're going to solve the ODE for IL of t because it's better to solve for capacitor voltages and inductor currents in our ODE rather than have to deal with integral equations rather than differential equations. And then later on, we can use this equation, the constitutive equation, to find VL of t. So we're going to go through a really big detour to find IL of t, and then at the end, we'll get VL of t rather quickly. So don't get thrown off by that. So that's how you add one extra step to the problem, is find either inductor current find capacitor current or inductor voltage. It adds just one step to the very end of your analysis. So by the characteristic equation, we get that 0 is equal to L over R times lambda plus 1. Or we get lambda is equal to negative R over L. So for our homogeneous solution, we'll get I sub L H of t is A e to the negative R over L t. And then we'll assume the particular solution is going to be B times e to the bt u of t, because we need to match this functional form. And we have an unknown coefficient B. Notice we specifically said that B is not equal to negative R over L. So we know that this exponential form does not match the exponential form of our homogeneous solution. Therefore, we do not need any t multipliers out front. We can just say it's B times e to the bt. If you weren't given this sort of condition about what the value of B is, you wouldn't be able to write a general solution to the differential equation using variables. You would be like, well, it's one of two options. And that's no fun. So let's specifically deal with the case where they are different bases of our exponent. So now we'll do some symbolic analysis. So we'll substitute I sub L of P d as a function of time into our ODE. So it'll show up right here. We have In of t is equal to I1 e to the bt u of t. And then we need to take the derivative of this expression to get this. So we're going to get a b times lowercase b times e to the bt u of t. So here we go. You get this equation right here. B times L over R times lowercase b e to the bt u of t. We get a copy of the particular solution at the end and our forcing function on the left-hand side. So we'll multiply through by e to the negative bt because all of our terms have it in common. And then we'll also consider for time t greater than 0. So all of these u of t's just become 1. And we'll get I1 is equal to b times the quantity L over R times b plus 1. When we deal with this. Or b is equal to I1 over 1 plus L over R times b. Notice the units check out. B has units, lowercase b has units of 1 over seconds. And L over R has units of seconds. So this is just a number in the denominator, which makes sense because we're adding them together. So our complete solution is just the particular solution in homogeneous solutions. So I1 over 1 plus L over RB times e to the bt u of t plus a e to the negative R over LT. Solve for A, knowing the circuit is at rest and inductor current cannot instantaneously change. We get 0 is equal to this coefficient times e to the 0 times 1, where e to the 0 times 1 is just 1. And then a times e to the 0 is just a. Or a is equal to negative I1 over 1 plus L over RB. So the opposite of what B was. So we will rewrite the complete solution to the inductor current in this form, where we have, I1 over 1 plus L over RB times the quantity e to the BT minus e to the negative R over LT times U of t. And then by the inductor constitutive equation, we need to multiply it by L and take the derivative. So we will get, well, this is just a constant, L times I1 over 1 plus L over RB times the derivative of e to the BT, which is just B times e to the BT. And then we'll get a plus R over L e to the negative R over LT, where again, our units make sense. Units of current times inductance gives us units of, well, magnetic flux in Webers. So, okay, you might have to stretch your physics knowledge a little bit. But if you take Webers and divide by units of time in seconds, you get volts. B has units of 1 over time, and R over L has units of 1 over time. So all your units work out in this equation for the inductor voltage. So now if we do an example, we'll say that, we'll have 0.1 amps times e to the negative 8 times 10 to the third 1 over seconds times t times U of t amps. And then we'll have a resistance of 1 kilo ohm and inductance of 10 millihenry. And then we find that lambda is equal to negative 1.0 times 10 to the fifth 1 over seconds. So our homogeneous solution looks like this. We know what our particular solution is going to look like. We're going to have this as our value of B. This is our value of A. When we plug in L over R and B and I1 into this, so we'll get, VL of T is equal to 1.08696 millivolt seconds, or milliweber if you are good about remembering your physics units, times the quantity 1.0 times 10 to the fifth 1 over seconds e to the negative t over 1.0 times 10 to the negative fifth seconds. That doesn't seem right. R over L. And, okay, that should be a positive in the denominator. Yeah, that should be 1.0 times 10 to the positive fifth seconds. That makes no. What? I was right. It's negative fifth seconds. I don't know what I'm saying sometimes. There's no error there. I thought this through. And then we'll have minus 8.3 times 10 to the third 1 over seconds times e to the negative 8 times 10 to the third seconds to the negative first time. All times U of t. That's a mouthful, but as you can see, that's how you would go about solving this type of problem. So you can see we can make life a lot harder for even a very simple parallel RL circuit by having a more and more complicated forcing function out front. So we can also apply, sinusoids. We could have multiple exponential decays represented in our, a sum of multiple exponential decays in our forcing function. And we can make the resulting equation very complicated very quickly. Okay, AJ had a question. B not equal to negative R over L is necessary. Well, Yeah, it would make this denominator 0, so it wouldn't make sense. But that's because it wouldn't match our forcing function term. Our forcing function, or not forcing function, our force solution term. Remember, we say if the forcing function is of the form e to the negative r over lt, we would have to include a multiplier of t out front, according to the special case written all the way back on slide 11. You would be expected to derive this if it was on an exam. So again, you should know how to get the ODEs very quickly, very quickly write out the ODE, go through the steps outlined. But like for the most part, you would be expected to basically do the steps the same way they were presented in the slides. Like we would make sure that you have, sufficient time to do this. However, that is, contingent on you having practiced these types of problems enough to be able to do them. So hopefully that answers your question, AJ and Riyadh. Oh, excuse me, everyone. My allergies are bad today. What questions do we have? This basically covers first order circuits, except for I made a plot of the numerical solution to VL of t. And as you can see, it reaches up to 100 volts. Graphically, it doesn't quite reach it, but that's because of a limit of the sampling of my plotting function. And then at time equals 54.9 microseconds, it reaches a minimum of negative 5.156 volts, and then it approaches 0 volts from below. So in this case, yes, you would have a negative voltage, but if you go back to the current would be a either positive or negative value. So I guess you can't make a strong statement one way or the other here. I guess one thing to note is if you've taken a class on differential equations and you did the circuit example, or you've done some circuits in physics, or you covered this in ECE 20001 and I missed out on it for some reason, you sometimes talk about time constants, tau, which is equal to -1 over lambda. So you sometimes talk about the time constants for an RC circuit, being -1 over lambda or positive R times C. And you sometimes talk about the time constant for a RL circuit as being positive L over R. And that way you're dealing with things in units of seconds. And then whenever you deal with your exponentials, it's always -t over tau, where tau is equal to RC or L over R, depending on your situation. It's just an alternate way of framing the same equations. Do we have any questions about RC and RL circuits? If not, I will move on and start teaching the LC circuit. So here is a series LC circuit. So now we're dealing with an inductor and capacitor in series with each other. So we're asked to find VC of t. So now we're going to have a root of the characteristic equation that is complex whenever we have multiple non-trivial reactive elements. So the result should be a sinusoidal solution instead of a pure exponential decay. So let's see this in action. We'll do the same stuff. So our constitutive equations are IC of t is equal to C dVc dt and VL of t is equal to L dIL dt. Again, these are basically the defining equations for what a capacitor and inductor are. They're as important as Ohm's law is for resistors. So by KVL and by knowing that IC of t is equal to IL of t, we write Vn of t the potential rise is equal to the sum of the potential drops in this complete loop. So Vn of t is equal to VL of t plus or Vc of t. So Vc of t just is as it is, but VL of t is L times dIL dt, and IL of t is the same thing as C times dVc dt. So you'll get L times C times the second derivative of Vc of t with respect to time. Now, when you write the characteristic equation, you'll get 0 is equal to LC times lambda squared plus 1. Move it, the 1 over to the other side, divide by LC, take the square root. We're taking the square root of a negative number. So we need to introduce the imaginary unit, j, where j squared is equal to -1. Remember, using the letter I is sacred for current. So we'll see that lambda is equal to plus or minus j times the square root of 1 over LC. So now we'll write the homogeneous solution as V sub CH of t is equal to A1 e to the plus j 1 over square root of LC t plus A2 e to the plus j 1 over square root of LC times t. And this is a perfectly valid formulation. You would get complex values for A1 and A2 if we were to try to solve this out completely, assuming the circuit is at rest. However, it's nice if we're working with real numbers because, every circuit element is a real number. We're dealing with real numbers for our, waveforms. It doesn't make sense to use complex numbers. So we'll use Euler's identity, where e to the j theta is equal to cosine theta plus j times sine theta to rewrite, this. So we'll get A1 cosine of t over square root of LC plus j times A1 times sine of t over square root of LC. And then very similar for this other term, where that should be a minus sign. I forgot that. That is an actual mistake. So A2 cosine of, a negative same thing, A2 sine of a negative argument. Now, if you remember your even and odd function identities for trigonometric functions, which hopefully you do, we're electrical engineers, we got to deal, or computer engineers, we got to deal with sinusoids all the time. Except for I think a couple of you that are not in electrical or computer engineering, but even still, we should know our even and odd trigonometric identities. So cosine of a negative thing is the same thing as positive cosine of the positive thing. And sine of a negative thing is equal to negative sine of the positive thing. So we can rewrite the homogeneous solution as B1 cosine of t over square root LC plus B2 sine of t over square root LC, where B1 is just, A1 plus A2, and B2 is just J times A1 minus A2. This is a perfectly valid thing. All we're doing is we're substituting one view with complex exponentials with another with purely real cosine and sine functions. So observe the homogeneous solution shows continuous oscillation of the voltage and current in the circuit. This will oscillate forever. Consistent for a reactive circuit, endlessly shifting energy between electric field storage in the capacitor and magnetic field storage in the inductor. All the energy is doing is going back and forth. There's no resistance to cause a dissipation of energy as losses in heat, or loss in the form of heat, I should say. We rewrote the homogeneous solution for a linear combination of complex exponentials to cosine and sine components because, again, we expect a purely real voltage because we're using real component values. Just like we used, the idea of, lambda or, as equal to this, and we introduced the idea of tau, the time constants, we'll define the natural frequency as omega naught equal to 1 over the square root of LC. And this will show up time and time and time and time again in this course. So you should definitely know how to find the natural frequency of a simple LC circuit or RLC circuit, like that. Shouldn't be any delay in your ability to spit out this simple equation. So is the radial frequency associated with the natural solution of the tank circuit ODE? So natural frequency plays a similar role to the time constants, tau is equal to RC and tau is L over R in the first order circuits we studied. What questions do we have? Is A2 missing a J in front? Oh, yes, you are correct. That should be a J in front of this A2 right there. 2 errors on the same slide. Sorry about that, everyone. All right. I am just going to call class here today. We'll get into the symbolic analysis, I guess, of the particular solution next time, because, it's involved enough that I don't want to start it and have to end partway through. I will take any final questions we have. Reminder, there will be another quiz this Friday. Don't wait to start working on your homework. And we're working on a survey that will allow you to practice using everything for the final thing. What are the applications of natural frequencies? Oh boy. I will say that there are so many that we will spend, most of lecture set 6 just talking about it. They're not lecture set 6. We'll spend lecture set 5 and lecture set 7 talking about them. It is going to, be a huge part of what goes on. Basically, if you've ever used a radio, this is how you tune to a certain, frequency of a radio station. I'll just say that is one example right there. Is W the same for parallel IC? I'm not sure what you're asking, Salem. Solon. Omega the same for a parallel IC or a parallel LC. When we look at the parallel LC later on, we will see omega naught shows up again. So, yep. Same for a parallel LC too. Thanks for directing my poor brain, Aubrey. All right. I think I've let you know what the course ahead is going to be like. Thank you all for attending today. It means a lot. Go forth. Enjoy the rest of your day. Bye, everyone. All right. Class is ending.